Imagine an invisible particle born from the death of a distant star passing through the sky, and in a single moment causing an aircraft cruising at an altitude of 12,000 meters to plunge downward. From that hypothesis, the perspective gradually expands into a quiet yet persistent connection between Earth and the depths of the universe. With each observation, consistent patterns begin to emerge. Fractures and strange structures on Europa suggest liquid water, moving beneath an ice shell once believed to be unchanging. Planets stretched around pulsars reveal the harsh power of gravity, and rare stellar explosions explain the origin of heavy elements that exist within the human body itself. Gradually, all of these merge into a seamless flow, where phenomena that seem unimaginably distant directly shape technology environments and the way humanity understands its fragile place in a vast but orderly universe. And next, we will explore the Kilonova, a remarkable phenomenon where the collapse of massive stars intersects with the collision of neutron stars, revealing key mysteries about energy-heavy matter and other profoundly enigmatic phenomena of the universe. The date was October 30th, 2025. At an altitude of 39,000 feet, the sky above the Gulf of Mexico appeared serene, an endless velvet blue stretching toward the horizon. Inside the cabin of JetBlue Flight 320, an Airbus A320 en route from Cancun to New York passengers were settling into the quiet rhythm of a routine flight. There was no turbulence on the radar, no mechanical warnings in the cockpit, and no hint of the cosmic violence about to intersect with their lives. Without warning, the laws of physics seemed to betray the vessel. The aircraft suffered a sudden violent loss of altitude, a plummet so sharp and unprovoked that it felt as if a colossal, invisible hand had reached down from the vacuum of space to crush the plane toward the Earth. Within seconds, the cabin was transformed into a scene of chaotic weightlessness. At least 15 passengers were hurled against the ceiling, and bulkheads suffering traumatic injuries as the pilots fought to regain control of a machine that had momentarily lost its mind. The pilots eventually stabilized the craft and made an emergency landing in Tampa, but the investigation that followed would uncover a chilling reality. This wasn't a failure of metal fuel or human skill, it was a digital assassination. An Airbus investigation later pointed toward a surge in solar radiation, as the culprit, a term that masks the true terrifying nature of our vulnerability. At 12 kilometers above sea level, the protective shield of Earth's atmosphere is dangerously thin, leaving modern avionics exposed to a rain of high-energy particles. But as the forensic analysis of the flight data began, a darker question emerged. Was the Sun truly the one who pulled the trigger? While the official statement blamed our local star, the cosmic evidence suggests we might be looking at a much more distant and far more powerful perpetrator. While the official report from Airbus pointed towards solar radiation as the culprit for the JetBlue 320 incident, the scientific community remained skeptical. The investigation had barely begun when Clive Dyer, a world-renowned specialist in space weather and cosmic radiation from the University of Surrey, stepped forward to challenge the narrative. To a cosmic detective, the solar alibi was weak on October 30th. The particle levels emanating from our Sun were entirely ordinary, nowhere near the threshold required to cripple high-altitude electronics. Dyer's counter-assessment shifted the gaze of the investigation millions of light-years away from our solar system. If the Sun was innocent, the bullet must have been a galactic cosmic ray, a stray particle from a distant supernova, or a supermassive black hole that had been travelling through the void for eons. When such a high-energy particle strikes Earth's upper atmosphere, it triggers a broad atmospheric shower, a cascade of secondary particles, muons, neutrons and positrons that rain down upon anything in their path. The threat at 12 kilometers is not just a theoretical concern for pilots. It is a statistical reality where radiation levels are 20 to 40 times higher than at sea level. For the passengers of Flight 320, the culprit was likely a single invisible neutron that bypassed the aircraft's shielding and struck a critical microchip. This is the single event upset, a digital ghost that flips a 0 to a 1, momentarily blinding the onboard computer and forcing the aircraft into a terrifying dive. As we stand on the threshold of a new era of aviation, these cosmic detectives warn that we're no longer just citizens of Earth. We are passengers in a high-energy firing range. To understand what happened in the cockpit that day, we must look beyond our atmosphere to the violent stars that share our galaxy. In the forensic world of avionics, a single event upset, or CU, is the ultimate phantom crime. It leaves no charred wires, no ruptured hydraulic lines, and no physical debris for investigators to collect. Yet as seen with the terrifying plunge of Flight 320, its effects can be catastrophic. To understand how a particle smaller than an atom can nearly down a 70-ton aircraft, one must look deep into the architecture of the silicon chips that govern modern flight. At its core, an SU is a malfunction caused by a single high-energy particle, typically a neutron or a proton striking a sensitive node within a microelectronic circuit. This phenomenon does not cause permanent physical damage to the hardware. Rather, it induces a state change in the data. In the binary language of computers, information is stored as bits of zeros and ones. When a cosmic particle collides with a transistor, it can leave a trail of ionization, creating a momentary current that flips a bit. A 0 suddenly becomes a 1, or a 1 becomes a 0. In the industry, this is known as a soft error. While a single bit flip might seem inconsequential, the context of the error is everything. If that bit resides in a non-critical file, the user might never notice. However, if that bit is part of the flight control computer's critical logic, the consequences are immediate. It can lead to what engineers call corrupted state machine logic. In such a scenario, the computer might incorrectly believe the aircraft is stalling or overspeeding, triggering an automated correction that the pilots did not command. This is precisely why Airbus was forced to suspend the flights of 6,000 A320 aircraft until a software update could be implemented to better filter out these erroneous signals. The vulnerability to SEUs is a direct result of the relentless march of technology. As we shrink transistors to make processors faster and more efficient, the amount of electric charge required to represent a bit becomes smaller. Consequently, it takes less energy from a cosmic ray to trigger a flip. We have built a civilization on silicon, but in doing so, we have created a nervous system that is increasingly sensitive to the radioactive pulse of the universe. On that October day over the Gulf of Mexico, a single particle, perhaps forged in a supernova millions of years ago, found a path through the aircraft's hull and struck a single transistor, proving that in the age of digital flight, the smallest ghost can cause the greatest fall. To identify the true assassin behind the sudden plunge of Flight 320, we must look far beyond the atmospheric envelope of our planet. While the Sun's activity was noted as a potential cause, experts like Clive Dyer have pointed the finger at a more elusive and ancient suspect: galactic cosmic rays. These are not rays in the traditional sense of light or radio waves, but high-velocity massive particles, mostly protons, electrons and atomic nuclei, travelling through the universe at nearly the speed of light. Their origin is a violent map of the cosmos, ranging from the shock waves of distant supernovae to the gravitational maws of supermassive black holes in the centres of far-off galaxies. When these particles, which may have been travelling for millions of years, finally encounter Earth, they find us sheltered behind a dual-layered defence system, the magnetosphere and the atmosphere. On the surface of the Earth, we are largely oblivious to this bombardment, as the thick blanket of air absorbs and deflects the brunt of the energy. However, for a civilian aircraft cruising at 12 kilometers, the rules of survival change. At this altitude, the air is significantly thinner, and the protective shielding is vastly reduced. Statistics reveal that radiation levels at these heights are 20 to 40 times higher than at sea level. Furthermore, flights crossing near the poles are exposed to 3 times more radiation than equatorial routes, as the Earth's magnetic field lines funnel particles toward the axis. The danger lies in the secondary effects. When a primary cosmic ray, a high-energy nucleus, strikes an oxygen or nitrogen molecule in the upper atmosphere, it doesn't just pass through. It shatters the molecule in a process called a broad atmospheric shower. This collision creates a cascading waterfall of secondary particles, muons, neutrons and positrons. It is these secondary ghosts that are the true threat to avionics. Unlike charged particles that can be deflected by magnetic fields, neutrons are electrically neutral and can penetrate the metal hull of an airplane with ease. In the case of Flight 320, a single neutron from such a shower likely found its way into the aircraft's flight control system. It was a freak coincidence of timing and geometry, a particle from an exploded star millions of light years away, colliding with a silicon chip at the exact microsecond required to flip a bit and send a plane full of people into a terrifying dive. This realization transforms our understanding of aviation safety. We are no longer just navigating winds and weather. We are navigating the radioactive debris of the deep universe. The terrifying plunge of Flight 320 is not an isolated anomaly in the history of aviation forensics. To a cosmic detective, the primary precedent for such a digital hijacking is the harrowing incident of Qantas Flight 72. In October 2008, an Airbus A330 was cruising over the Indian Ocean, travelling from Singapore to Perth, when it suddenly and violently lost altitude without any mechanical warning. Like the JetBlue incident, this event was characterised by a suddenness that defied conventional explanations of turbulence or pilot error. The force of the descent was so extreme that passengers experienced several seconds of total weightlessness, mirroring the parabolic flight paths used to train astronauts. During these intervals, unbuckled passengers were hurled into the ceiling of the cabin, resulting in a grim scene of broken bones, lacerations, and structural damage to the aircraft interior. The flight suffered two distinct sharp drops, leaving the crew and passengers in a state of terror as they struggled to understand why the fly-by-wire system had turned against them. Investigations into Qantas 72 eventually pointed toward a malfunction in the Air Data Inertial Reference Unit. The computer began receiving spikes of erratic data, which the system interpreted as a critical flight emergency, triggering an automated nose-down command. Expert Clive Dyer has frequently cited this case as a prime example of where a high-energy cosmic particle may have been the silent instigator. Just like the Sioux suspected in Flight 320, a single neutron striking a specific memory cell in the navigation computer could have created the ghost data that misled the entire aircraft. These historical echoes reveal a pattern of vulnerability in the digital architecture of modern flight. While aviation engineers have built incredibly redundant systems to handle mechanical failures, the threat from the vacuum of space remains a wild card. The case of Qantas 72 stands as a cold reminder that the higher we fly and the more complex our electronics become, the more we expose ourselves to the invisible projectiles of the cosmos. This history of near disasters has paved the way for a new philosophy in aircraft design, moving towards systems that are not just mechanically sound, but cosmically resilient. To mitigate the threat of cosmic radiation, the aviation industry must balance the laws of physics with the constraints of engineering. Unlike spacecraft operating in the harsh vacuum of the deep void, civilian aircraft remain partially shielded by the Earth's magnetosphere and the residual atmosphere. Consequently, installing massive lead-heavy physical shielding is not only impractical for flight efficiency, but also unnecessary. Instead, the defense against these invisible assassins is being fought on two primary fronts: hardware hardening and intelligent software logic. Hardware-based solutions involve manufacturing electronic components that are inherently more resistant to the ionizing effects of high-energy particles. This process, often referred to as radiation hardening, involves using specialized materials or redundant circuit designs where multiple transistors perform the same calculation. If a cosmic particle strikes one node and causes a bit flip, the other nodes provide a majority vote to override the error, ensuring the system maintains its integrity. By designing chips with larger transistors or specialized insulator on silicon substrates, engineers can raise the energy threshold required for a single particle to induce a state change. However, the most agile line of defense lies in the software code itself. Following the investigation into recent altitude loss incidents, the focus has shifted toward updating the flight control software to identify and ignore data spikes caused by single event upsets. Modern software protocols are being programmed to recognize that a sudden physically impossible change in sensor data, such as a plane supposedly diving thousands of feet in a microsecond, is likely a digital glitch rather than a reality. By implementing these filters, the onboard computers can effectively reboot or discard the corrupted data bit before it ever reaches the mechanical actuators of the wings. Through this combination of resilient hardware and sophisticated logic, we are teaching our machines to survive in an environment where the very sky is a firing range for the stars. While investigators on Earth analyze the invisible ghosts of cosmic rays, planetary scientists have turned their gaze toward the icy surface of Jupiter's moon Europa to solve a different kind of mystery. At first glance, the surfaces of many moons in our solar system appear desolate and covered in craters, but Europa is a geological masterpiece of activity and youth. Among its many features, one specific location stands out to the cosmic detectives of NASA and the ESA, the Mannanen crater. Mannanen is a relatively large impact crater measuring approximately 22 kilometers in diameter. It was primary data from the Galileo spacecraft, which explored the Jovian system from 1995 to 2003, that first revealed a terrifyingly beautiful anomaly at the heart of this impact site. Right at the centre of Mannanan, scientists discovered a dark complex structure that looks remarkably like a giant spider or a sprawling snowflake. This spider of Europa consists of a dark central core with numerous branching legs or rays radiating outward in every direction. The presence of such a feature is highly unusual because Europa's surface is mostly composed of a thick, rigid shell of water ice, often miles deep. Under normal circumstances, an impact should simply leave a bowl-shaped depression. However, the spider suggests that the collision which created Mannanan did more than just crater the surface. It acted as a violent catalyst that triggered a surge of material from beneath the crust. Because Europa is believed to harbour a vast subsurface ocean of liquid water, the Mannanan craters become a primary crime scene for understanding how internal water interacts with the external frozen shell. Due to the limited resolution of the aging Galileo images, the fine details of these branching rays remain shrouded in mystery. Nevertheless, the structure provides a vital clue to the Moon's hidden dynamics. To solve the riddle of what formed this spider, researchers must look for terrestrial analogues and compare the Mannanan impact to other mysterious arachnids found across the solar system. To explain the haunting anatomy of the spider at the heart of the Mannanan crater, researchers have looked toward the subsurface chemistry of Europa. While the Moon's ice shell is several kilometers thick, it is far from a solid static block. Scientific models suggest that within this frozen crust there exist localized brine pockets, reservoirs of liquid water with a high concentration of salts. These salts act as an antifreeze, allowing the water to remain liquid, even at temperatures far below the freezing point of pure water. The formation of the spider-like feature likely began with the impact itself. When a large object struck the surface to create Mannanan, the resulting energy did more than just excavate a bowl. It generated immense heat that melted a significant portion of the ice beneath the impact point, creating a temporary localized pocket of liquid water at a shallow depth. As this water began to refreeze over time, its volume expanded, creating a massive buildup of upward pressure against the overlying ice. This pressure eventually reached a breaking point, causing the surface ice to rupture. The pressurized salty water or brine was forced upward through the cracks, erupting onto the surface and flowing outward into a slushy, porous layer of material created by the impact's debris. As the brine moved, it followed the path of least resistance, branching out into the intricate dendritic patterns we now observe as the spider's legs. This process is closely related to lenticulae, the various pits, domes, and dark spots that pepper Europa's surface. These features are thought to be the surface manifestations of internal heat and material rising through the ice. In the case of Mannanan, the impact provided the perfect catalyst for this brine eruption. Experimental simulations in laboratories have successfully recreated these concentric branching structures by forcing salty water through simulated Jovian ice, reinforcing the theory that the spider is a frozen record of a subterranean surge. To truly decode the mystery of the structure in Europa's Mannanan crater, cosmic detectives look for similar fingerprints across the solar system. The most famous relatives of the Jovian spider are the spiders of Mars, located in the red planet's south polar regions. However, the physical mechanism behind these two phenomena reveals a fascinating divergence in planetary behaviour. On Mars, these branching structures, technically known as areniforms, are driven by the seasonal sublimation of carbon dioxide ice. When sunlight penetrates the translucent dry ice, it heats the dark soil beneath, causing the CO2 at the base to turn directly into gas. This trapped pressure eventually erupts through the ice, scouring the surface and creating the spider-like channels. Europa, however, presents a different environment. Unlike Mars, Europa has no dark soil layer directly beneath a thin film of ice. Its crust is a massive deep layer of water ice. Consequently, the Martian model of gas sublimation does not apply. Instead, scientists have found a more accurate terrestrial analogy: lake stars, or ice stars, found on frozen ponds on Earth. On Earth, these stars form when a small hole appears in relatively thin ice covered by a layer of slushy snow. Relatively warmer water from below is forced through the hole, spreading outward and melting the slush into a dendritic branching pattern before refreezing. The spider of Mannanan is essentially a cosmic version of these Earth stars. The impact that created the crater acted as the initial hole maker, while the subsurface brine pocket provided the warmer pressurized liquid. This comparison allows scientists to reconstruct the event an impactor strikes, creates a temporary atmosphere and a slushy surface layer, and triggers a localized upwelling of salty water that carves the legs of the spider into the icy terrain. By bridging the gap between a frozen lake on Earth and a crater 600 million kilometers away, researchers have turned a celestial anomaly into a predictable result of planetary physics. The presence of the spider within the Mannanen crater serves as more than just a geological curiosity. It acts as a window into the most tantalizing feature of the Jovian moon, its global subsurface ocean. While the surface of Europa is a frozen wasteland of water, ice scientists are increasingly certain that a vast liquid ocean exists beneath that shell, containing more water than all of Earth's oceans combined. The spider provides indirect proof of this hidden world by demonstrating that liquid water, or at least pockets of pressurized brine, can still reach the surface in the moon's relatively recent history. This oceanic environment is the primary reason Europa is considered a top candidate in the search for extraterrestrial life. Life as we understand it requires three essential ingredients: liquid water, essential chemical elements, and a source of energy. Europa's ocean likely meets all three. The liquid water is maintained by tidal heating, the constant stretching and squeezing of the moon by Jupiter's immense gravity, which generates internal friction and heat. If this heat also powers hydrothermal vents on the ocean floor, it could provide the chemical energy necessary for life to thrive in total darkness, independent of sunlight. The spider structure suggests that the impact which formed the Mannanen crater created a temporary highway for material to move between the ocean and the surface. If life exists in Europa's depths, it is possible that organic molecules or even biological markers were carried upward during the brine eruption that formed the spider's branching legs. By studying these surface features, scientists are effectively performing a forensic analysis of the ocean below without having to drill through kilometers of ice. Every crack ridge and chaos region on Europa tells a story of an active world where the deep ocean is constantly trying to break through its icy cage. The Mannanen spider is a frozen scream of that activity, a sign that the deep, dark waters of Europa are not just sterile but dynamic and potentially pregnant with the building blocks of life. The mystery of the Mannanen spider and the potential for life within Europa's depths will not remain unsolved for long. Humanity is currently launching a sophisticated multi-platform investigation to decode the secrets of the Jovian system. Two flagship missions, NASA's Europa Clipper and the European Space Agency's JUICE, are currently traversing the cold void of space to provide the high-resolution data that the aging Galileo spacecraft could never capture. The Europa Clipper mission is specifically designed to perform dozens of close flybys of the icy moon. Equipped with advanced cameras and ice-penetrating radar, Clipper will scan the Mannanen crater with unprecedented precision, allowing scientists to see the fine structure of the spider's legs and determine their chemical composition. By measuring the thickness of the ice shell and the depth of the ocean below, the mission will confirm whether the brine eruption model truly explains the features we observe. Simultaneously, the Jupiter Icy Moons Explorer, or JUICE, will conduct a broader survey of the Jovian neighborhood. While its primary focus includes Callisto and Ganymede, JUICE will provide critical contextual data on Jupiter's intense radiation environment and the tidal forces that pump heat into Europa's core. Together, these missions represent the pinnacle of modern cosmic detective work. We are no longer limited to blurry snapshots from the 1990s. By the early 2030s, when these probes arrive at their destination, the enigmatic spider of Mannanen will be unmasked, potentially revealing the first definitive proof of an environment capable of sustaining life beyond Earth. In our cosmic investigation, we often encounter worlds that defy the standard spherical expectations of planetary physics. One of the most extreme cases recently scrutinized by the James Webb Space Telescope is the exoplanet PSR J23266b. This world does not orbit a life-giving sun. Instead, it circles a pulsar, the hyperdense, rapidly spinning corpse of a massive star that ended its life in a supernova. Because pulsars emit a significant portion of their energy in the invisible gamma-ray spectrum, the infrared eyes of the James Webb Telescope were able to observe this planet more clearly than many others orbiting normal stars. The environment of PSR J2326650b is a study in physical violence. The planet is locked in an orbit 100 times closer to its pulsar than the Earth is to the Sun, completing a full year in less than 8 hours. At such a terrifyingly close proximity, the planet is subjected to the absolute limits of tidal forces. These are not the gentle tides that move Earth's oceans. These are gravitational gradients so powerful that they overcome the planet's own self-gravity. The result is a total structural distortion. The gas giant is stretched and squeezed into an elongated shape resembling a lemon or a rugby ball. The lemon planet is a unique anomaly in our database. It is the only known planet with a mass comparable to Jupiter, found in such an extreme close-quarter orbit around a pulsar. To a scientist, this shape is a frozen scream of the immense energy at work. The tidal forces act like an invisible cosmic vice constantly pulling at the planet's atmosphere and core. This proximity to a pulsar also subjects the planet to intense radiation, which has stripped away its original hydrogen and helium, leaving behind a bizarre chemical signature. As we profile this distorted world, it serves as a grim reminder of the destructive power of stellar remnants. In the vicinity of a pulsar, the classical image of a planet as a stable round haven is obliterated. PSR J2322+6 is a victim of its own geography, a world being slowly torn apart and reshaped by the gravity of a dead star, proving that in the deep universe, geometry is dictated by the most brutal forces imaginable. The physical distortion of PSR J2322+6 is only the beginning of its strangeness. Its chemical profile is equally alien. While most gas giants in our galaxy are composed primarily of hydrogen and helium, the atmosphere of this lemon-shaped world is dominated by much heavier and darker elements. Observations from the James Webb Space Telescope have revealed an atmosphere saturated with helium, and most notably molecular carbon. This unique composition is a direct consequence of its proximity to the pulsar, whose intense radiation has likely stripped away the lighter gases over eons, leaving behind a concentrated noir cocktail of carbon-based compounds. The climate of this world is a nightmare of extreme chemistry. Vast thick clouds of soot, pure carbon particles drift through the upper atmosphere, blotting out what little infrared light reaches the planet. These soot clouds create a permanent pitch-black shroud, making the planet a dark mirror to the pulsar's violent energy. However, as one descends deeper into the crushing pressures of the planet's interior, the chemistry undergoes a radical transformation. The immense atmospheric weight forces the carbon atoms to rearrange their structure, transitioning from soot and graphite into crystalline form. In these deep high-pressure layers, scientists believe it literally rains diamonds. These are not the small gems found in jewelry stores on Earth, but massive hailstones of pure diamond falling through a sea of liquid helium. This phenomenon, while theorized on other gas giants like Neptune, reaches a pinnacle of intensity on PSR J23+650b due to the extreme gravitational squeezing it endures from its pulsar host. The origin of such a world remains a mystery that continues to challenge our models of planetary formation. It is a place where the air is made of smoke and the rain is made of treasure, a world forged in the aftermath of a star's death, proving that the universe's most beautiful materials are often created in its most violent crucibles. While the lemon-shaped world of PSR J232+650b showcases the brutality of dead stars, our cosmic investigation also reveals Tatooine-like planets that survive within the complex gravity of binary star systems. These rare worlds, reminiscent of the fictional home of Luke Skywalker, orbit two suns simultaneously. In such systems, a planet has two primary survival strategies. It can either orbit one of the stars individually, or move in a wide circumbinary orbit around the pair. Recent forensic work using archival data from the Gemini South Telescope has uncovered a particularly striking example. This planet orbits its twin suns 6 times closer than any other known circumbinary world, yet its year, one full revolution, still takes a staggering 300 Earth years to complete. Scientists were able to capture this world through direct imaging, using a coronagraph to mask the blinding light of the central stars, revealing the planet as a distinct moving speck of light. The existence of these worlds remains a profound mystery for planetary architects. The gravitational turbulence caused by two suns should in theory shred a forming planet or eject it into the frozen void of interstellar space. Yet these Tatooine worlds persist, proving that stable orbits can emerge even from the most chaotic stellar dances. As we profile these systems, we realize that the standard model of a single sun solar system is just one of many ways the universe organizes itself. Each newly discovered binary system forces us to recalibrate our understanding of where and how a world can truly call home. In the traditional records of astronomy, a star's death is a singular final event, the collapse of a core into a solitary remnant. However, a groundbreaking discovery in August 2025 has forced scientists to introduce a radical new suspect into the cosmic archives, the Kilonova. This phenomenon arises from an extraordinary process known as stellar fission, where a star, instead of simply exploding, undergoes a violent act of self-division. The investigation began when the LIGO, Virgo and Kagra observatories detected a gravitational wave signal from a source 3 billion light-years away. To the shock of the cosmic detectives, the mass of the colliding objects was calculated to be unexpectedly low, less than that of our Sun. Standard models of stellar evolution dictate that a neutron star should be at least 1.2 to 1.4 times the mass of the Sun. A sub-solar mass object seemed physically impossible unless a new mechanism of birth was at work. The leading hypothesis suggests that when a massive, rapidly rotating star begins its final collapse, the extreme centrifugal forces overcome the pull of gravity. Instead of forming one core, the star's heart is literally torn apart into two distinct smaller fragments. This is stellar fission, a celestial budding process where a single progenitor star gives birth to a pair of low-mass neutron stars. These twin cores are born in a tight, frantic dance, orbiting a common center of mass, while still encased within the exploding shell of the original supernova. This Kilonova scenario explains the bizarre double identity of the August 2025 event. For the first few days, telescopes observed a rapidly fading red glow, characteristic of a kilonova, the collision of two neutron stars. But soon the signal shifted, turning blue and behaving like a Type Cent2b supernova, the signature of a collapsing massive star. The superkilonova is the bridge between these two worlds, a star that explodes as a supernova, only to have its newly born twins collide and explode again as a kilonova within the very same wreckage. The discovery of the superkilonova represents a triumph for multi-messenger astronomy, a modern holy grail for cosmic detectives. Traditional astronomy relied almost exclusively on electromagnetic waves, visible light, radio and X-rays to observe the universe. However, to solve the mystery of objects with masses lower than our Sun, scientists required a combination of at least two out of the four primary channels: electromagnetic radiation, neutrinos, cosmic rays and gravitational waves. By analysing signals from multiple channels simultaneously, researchers can achieve a much deeper understanding of a single event. The investigation into the August 2025 event was triggered by the detection of gravitational waves ripples in the fabric of spacetime caused by the collision of massive compact objects. When the LIGO, Virgo and Kagra observatories captured the signal, they utilised triangulation to determine its location in the sky, much like how human ears locate a sound. This allowed telescopes to pivot within hours to find a rapidly fading red object, 1.3 billion light-years away. The multi-messenger data revealed a startling contradiction. While the light suggested a kilonova followed by a supernova, the gravitational wave signature calculated a mass that was unexpectedly low. This subsolar mass signature is the smoking gun for the stellar fission theory. In standard scenarios, a neutron star remains above 1.2 solar masses. However, if a star's core splits during collapse, it can produce stable neutron star fragments of only 0.5 to 0.8 solar masses. This solves a long-standing mystery in the cosmic archives: how such featherweight neutron stars can exist at all. Without the gravitational wave channel, scientists would have only seen the light of the explosion and missed the structural anomaly of the colliding twins entirely. By combining the sound of spacetime with the sight of light, the superkilonova has been unmasked not as a mistake in measurement, but as a new type of cosmic event. This multi-channel approach has effectively turned the universe into a laboratory where the most extreme laws of physics are finally being observed in real time. We're no longer just watching the stars, we are listening to their heartbeat and feeling the shockwaves of their most violent transformations. The superkilonova is more than just a rare celestial event. It is the universe's most prolific divine mint. While standard stars spend billions of years fusing light elements like hydrogen and helium, the creation of heavy precious metals such as gold, platinum and uranium requires a much more violent and neutron-rich environment. The stellar fission event leading to the collision of two low-mass neutron stars provides the perfect laboratory for a process known as rapid neutron capture, or the R process. During the milliseconds of the collision, the extreme heat and density reach a point where atomic nuclei are bombarded by an overwhelming flux of free neutrons, In this frantic environment, nuclei grow larger and heavier faster than they can decay, effectively forging heavy elements out of the raw subatomic debris. The specific spectral signature of the August 2025 event, captured by the Keck Observatory, revealed a rapidly fading red glow, the unmistakable fingerprint of heavy element production. This super kilonova represents a massive output of wealth on a galactic scale. A single event can produce a mass of gold several times larger than the Earth itself, which is then blasted into interstellar space by the force of the combined kilonova and supernova explosions. Eventually, these precious atoms settle into clouds of gas and dust, becoming the building blocks for the next generation of planets. Every gold ring on a human finger and every gram of platinum in our technology was likely minted in such a violent crucible billions of years ago. By studying the super kilonova, we are not just observing a distant explosion. We are looking at the ancient factory that manufactured the very atoms of our modern world. The history of our quest to decode the universe is not only written in the light of distant stars but also in the meticulous corrections of human error. No instrument embodies this struggle more than the Hubble Space Telescope, a legend of modern astronomy that nearly became a billion-dollar monument to failure. When it was first launched in 1990, the scientific community expected to see the birth of galaxies. Instead, they were met with blurred, ghostly halos. The most sophisticated eye ever built was nearsighted. The forensic investigation into Hubble's blurry vision revealed a staggering truth: the primary mirror had been polished to the wrong shape. The deviation was a mere 2.2 micrometers a distance, approximately 50th the width of a single human hair. This microscopic flaw, invisible to the naked eye, was enough to scatter the light of the cosmos, rendering the telescope's ambitious mission impossible. It was a chilling reminder that in the realm of high-precision science there is no such thing as a small mistake. To save, the mission engineers had to design the Corrective Optics Space Telescope Axial Replacement, or COSTAR. Effectively acting as a pair of contact lenses for the telescope, COSTAR was installed by astronauts in 1993 during one of the most complex orbital repair missions in history. The fix was a triumph of human ingenuity. Once the lenses were in place, the universe snapped into sharp focus, revealing the breathtaking pillars of creation and the deep fields of gravity we study today. The lesson of Hubble serves as a vital bridge to our current understanding of phenomena like the super kilonova or the invisible particles striking our aircraft. Just as a microscopic error in a mirror could blind us to the stars, a single bit flip in a silicon chip can bring down a jet. Our modern world is built on a foundation of extreme precision, where the difference between a groundbreaking discovery and a catastrophic failure often rests on a scale smaller than a human hair. By correcting Hubble, we did more than just fix a telescope. We proved that humanity possesses the resilience to refine its vision and find clarity within the most complex mysteries of the void. As we conclude this investigation into the violent mechanics of the cosmos, from the subatomic bullets striking our aircraft to the apocalyptic birth of super kilonovae, it is easy to feel small and vulnerable. We inhabit a universe where a single particle from an exploded star millions of light years away can reach through our atmosphere and momentarily hijack a 70-ton machine. We live in a reality where gravity is so brutal it can vat an entire planet into the shape of a lemon. Yet the true revelation of modern science is not just the scale of these threats, but our increasing ability to understand and predict them. By studying the spiders on Europa's frozen shell, we are learning to read the history of hidden oceans. By analysing the double identity of colliding stars, we are discovering the very origin of the gold that we treasure on Earth. Each of these events, however chaotic they may seem, follows the strict and beautiful logic of physics. The story of the JetBlue 320 incident, or the blurred lens of the Hubble telescope, reminds us that our civilization is a high-precision instrument. We are constantly refining our vision, moving from blurry confusion to a sharp, multi-channel understanding of the void. Despite the cosmic scares that make headlines, the rogue black holes, the solar storms, and the vacuum decay, we remain shielded by a delicate balance of planetary defense and human ingenuity. As we look toward the future, the most profound wish we can harbor is for normality. In a universe defined by extreme explosions and gravitational distortions, the stable orbit of our Earth and the predictable rhythm of our lives are the ultimate anomalies. We are the children of stardust born from the debris of Kilonovae, and it is our curiosity that turns the terrifying unknown into a map of discovery. As the next generation of telescopes and probes like the Europa Clipper prepare to launch, we continue our journey not as victims of the universe, but as its most observant detectives. As we close the file on these cosmic mysteries, we are reminded that the universe is not a distant, silent backdrop, but a dynamic and often violent protagonist in our own history. From the invisible particles that challenge our digital safety at 39,000 feet, to the majestic heavy metal forges of a super Kilonova, every discovery brings us closer to understanding our place in the void. We are living in a golden age of multi-messenger astronomy, where for the first time we can hear the vibrations of space-time and see the birth of elements simultaneously. As missions like Europa Clipper and JUICE prepare to unmask the secrets of icy moons, our role as observers remains the same: to turn curiosity into clarity. The stars may be indifferent to our existence, but our ability to decode their signals is what makes us truly human. Thank you for journeying through the extreme limits of physics with us. Until our next investigation, keep looking up, because the answers to our future are written in the light of the ancient past.